Yeah, good morning, my dear students. So today I am going to discuss the topic on various important organic bands of functional groups in IR spectra. First of all, we should compare different groups also here. The first one is alkanes. The alkanes are having the carbon-hydrogen stretching vibration. CH stretching vibration will be coming at 2960 to 2870 centimeter inverse, whereas the CH bending vibration will be coming at 1450 centimeter inverse, especially the outer plane bending vibration. Similarly, for alkenes, the double bonded compounds, the CH stretching vibration will be coming at 3080 to 2990 centimeter inverse, whereas the bending CH bending vibrational group will be coming at 890 centimeter inverse. And if you look at alkynes, C triple bond C stretching, the CH stretching vibration will be coming at 3300 centimeter inverse, and the CH bending vibration will be coming at 680 to 620 centimeter inverse. So if you compare alkanes, alkenes and alkynes, so alkynes will be having the higher stretching vibration as compared with alkenes, as compared with alkanes. Whereas the bending vibration for alkanes is higher, then alkenes is little lower. That is, alkanes is half of the stretching vibration is equivalent to bending vibration in alkanes. Whereas if you look at here, it is around 1/3 will be the bending vibration here for alkenes. And for alkynes, it will be around 1/4 or 1/5 of the bending vibration for alkynes, right? So definitely 1450, 890 and 680 centimeter inverse. So this is the way we are comparing the various bands of organic functional groups between alkanes, alkenes and alkynes. Now next important aspect is aromatic compounds and phenols. When we discuss about aromatic stretching vibration, the CH stretching vibration will be coming between 3080 to 3030 centimeter inverse, whereas the CH bending vibration is from 900 to 680 centimeter inverse, preferably the outer plane bending vibration. Now when I compare with this phenol, the hydroxyl group is present extra in phenol. The hydroxyl stretching vibration will be coming at 3600 centimeter inverse, whereas the carbon oxygen stretch vibration in the phenol will be coming at 1220 centimeter inverse. And the hydroxyl bending vibration for phenol will be roughly around 1360 centimeter inverse. Now this is a classical difference between aromatic compounds as well as your phenols. Now next important compounds are aldehydes, ketones, acids and ether. They belong to similar category. So when I discuss about aldehyde group, the CH stretching vibration of aldehyde will be coming between 2820 to 2700 centimeter inverse, whereas the CH bending vibration will be coming at 1390 centimeter inverse. The very important group for aldehyde stretching vibration, that is carbonyl stretch vibration of the aldehyde, will be coming at 1730 centimeter inverse. Now coming to ketone, the carbonyl stretch vibration will be coming at 1715 centimeter inverse. There is a minute variation. Now coming to acid group, the acid group contains the COOH, right? The hydroxyl group of the acid. The hydroxyl stretch vibration of the acid will be coming in the region of 3000 to 2500. See, generally the hydroxyl stretching vibration will be coming around 3600, but in case of acid it will be lowered 3000 to 2500 because of intramolecular hydrogen bonding. So whenever the hydrogen bonding takes place within the molecule, definitely the vibrational frequency will be affected and it comes in the lower region. That is why for hydroxyl stretch vibration of the acid will be coming between 3000 to 2500 centimeter inverse. The carbonyl stretch vibration of that will be coming at 1710 centimeter inverse, and the bending vibration of hydroxyl group of acids will be coming with the two regions, or the dimer will be there, one at 1420 centimeter inverse and the other at 925 centimeter inverse. And coming to ether, the carbonyl stretch vibration of the ether will be giving two respective bands at 1100 centimeter inverse and 860 centimeter inverse. So this is the way we can compare the aldehyde, ketone, acid and ether group, right? So the next important is amines. When we talk about the amines, there are three classes of amines: primary amines, secondary amines and tertiary amines. So primary amines, the NH stretching vibration will be coming at 3400 to 3300 centimeter inverse, and the bending vibration NH will be coming at 1610 centimeter inverse, right? And the very important thing, the carbon nitrogen stretch vibration of the primary amine will be coming at 1065 centimeter inverse. Now coming to the secondary amines, the NH stretch vibration will be coming at 3330 centimeter inverse. the bending vibration is almost similar, 1006 centimeter inverse, whereas the carbon nitrogen stretch vibration you will be getting as a dimer, one at 1150 centimeter inverse and the other at 850 centimeter inverse. Now coming to the tertiary amines, there is no NH group, so there is no stretching vibration because only carbon and nitrogen will be there, and there is no NH will be there, therefore no bending vibration. Only the carbon nitrogen stretch vibration will be there at a very lower frequency, 780 centimeter inverse. So this is how we can classify or differentiate the primary amine, secondary amine and the tertiary amines with the help of IR functional groups. Now coming to the alcohols, alcohols also having three categories: primary alcohol, secondary alcohol and tertiary alcohol. If you look at primary alcohol, the hydroxyl stretch vibration of primary alcohol will be coming at 3635 centimeter inverse, whereas the bending vibration will be coming at 1300 centimeter inverse, whereas the carbonyl stretch vibration of primary alcohol will be coming at 1050 centimeter inverse and 850 centimeter inverse. Now if you go for tertiary alcohol, the tertiary alcohol hydroxyl stretch vibration will be coming at 3625 centimeter inverse. The bending vibration remains same. The carbonyl stretch vibration, CO stretch vibration of secondary alcohol will be coming little lower. That means 1050 in primary, now it becomes 1100, whereas the other one 850 in the primary alcohol, it will be reduced to 830 centimeter inverse. Now if you take the tertiary alcohol, the hydroxyl stretch vibration will be 3615 centimeter inverse. The bending vibration hydroxyl group will be 1300 centimeter inverse, whereas the CO stretch vibration of tertiary alcohol will be coming at 1150 centimeter inverse and 780 centimeter inverse. So only these region, the carbonyl stretch vibration, especially for the amines, these three regions are very very important to segregate them. Similarly for alcohols, the carbonyl stretch vibration are very very important to segregate the particular functional groups for alcohols as such, right? So this is a very important aspect. Similarly, if you go for the chloroalkanes or haloalkanes, the carbon with the chlorine stretch vibration, that will be coming in the region of 850 to 550 centimeter inverse, because when we attach the heavy atoms like chlorine, definitely there have the reduced mass of the system will be very high, so automatically the stretching vibration itself will be coming in the lower region of the IR spectra. So these are the important functional groups of selective compounds, particularly alkanes, alkenes, alkynes, aromatics and phenols, aldehydes, ketones, acid and ether, then amines and alcohols. Now there are certain factors which are affecting the vibrational pattern, right? What are all the various factors? During this bands of functional groups, when we discussed, I told about the hydrogen bonding. When we have the hydrogen bonding interactions within the molecule, definitely what will happen, the vibrational frequency will be reduced, as we have seen in the case of the hydroxyl stretch vibration in acid, right? Because in acid group, the hydroxyl stretch vibration will undergo the intramolecular hydrogen bonding, right? So like other factors are also there. One of the important aspect is that the vibrational bands of hydroxyl group, NH group and carbonyl bands, right? They are strong in the IR spectra, right? And they are making the ideal technique to study the hydrogen bonding. Similarly, the amide groups, which are commonly found in the drug molecules, and the position of the amide group, particularly the NH and the carbonyl stretch modes in the IR spectra, is useful to identify the inter and the intramolecular hydrogen bonding pattern, right? Some other factors are also there. Hydroxyl vibration, OH vibration, the exact position of the bands depend upon the extent of hydrogen bonding. That is, lower the vibrational hydroxyl frequency, the stronger the hydrogen bonding, as I told in case of acid. If you have the stronger hydrogen bonding interaction, the vibrational frequency of the hydroxyl group will be reduced, right? Originally the hydroxyl group free stretching vibration will be coming at 3600, but in case of acid it will be coming from 3000 to 2500. It is reduced. Why? Because of intramolecular hydrogen bonding, right? So more than one band absorbed, each hydrogen is involved in different hydrogen bonds, right? That is higher hydrates like magnesium sulfate and with 7 molecules of water, we call them as Epsom salt. So if you have more number of water molecules, so the band whatever you are getting in the IR spectra, so that will be more than one as such, depending upon the number of water molecules attached with the substance, right? Particularly in the form of hydrates, water of crystallization, right? If the hydrated sample is heated, Suppose if you are heating the hydrated sample, Epsom salt, if you are heating it, so what will happen? The intensity of the 3640 centimeter inverse band is reduced as the water level decreased. If you are heating that, what will happen? Wherever the hydroxyl band will be produced, 3640 centimeter inverse, the band intensity, the peak intensity will be reduced. Suppose if the peak is like this, now the peak intensity will be reduced like this, right? The band intensity will be reduced, particularly when the if you are heating the molecule containing water, right? And similarly, if you have amorphous and crystalline solids, for amorphous solids, crystalline solids are having the perfect arrangement, right? So what will happen? In amorphous solids, they have the increased bandwidth in the IR spectrum. Increased bandwidth in the sense, you will be having the bandwidth like this, right? It is an increased bandwidth. Whereas for crystalline sand solids, we have the decreased bandwidth in the IR spectra. It will be very sharp as such, right? So crystalline solids are having the perfect arrangement of geometry, whereas in amorphous solids, they have the randomness. Therefore, the bandwidth will be very high for amorphous solids, whereas the bandwidth will be little lesser in case of crystalline solids, right? And what is the effect of conjugation in IR absorption band? One of the simple example is carbonyl group I am taking here. The carbonyl group of aldehydes and ketones, if I am taking, the electrons present in the carbonyl group are very firmly present because they are very solid, or they are very fixed. These electrons are very firmly based. So if we introduce the conjugation with this carbonyl group, now those electrons can delocalize over 3 to 4 atoms, or sometimes even more also, right? So what will happen if these electrons present in the double bonded O, carbon double bond O, these electrons are very permanently fixed, right? If you introduce the conjugation, what will happen? These electrons are delocalized to next 3 to 4 atoms, or sometimes even to more than 4 atoms, right? So such cases, what will happen? This weakens the carbonyl band, right? This weakens the carbonyl bond. C double bond O bond will be weakened, moving the IR peak down to lower vibrational frequency. Because of this, what will happen? The vibrational frequency will be reduced. So if you are having more and more conjugation with the functional groups like C double bond O, again the vibrational frequency will be reduced, right? So this is the very important aspect. Similarly, the effect of hydrogen bonding in the IR absorption band, I already discussed the example of acid group. So if you take pyrazine molecule with water, right? So the stretching vibration will be coming at 3048 centimeter inverse, and the out of plane bending vibration will be coming with 931 centimeter inverse. So the hydrogen bonding decreases the bond absorption, as we discussed already, right? So hydrogen bonding as well as conjugation, when we are attaching with this bands, so what will happen? The vibrational frequency will be reduced. So these are the important factors involved in IR spectra, particularly with related to hydrogen bonding and conjugation, right? So this is all about the factors affecting vibrational pattern and what are all the important organic bands of functional groups in IR spectra. I hope it is clear. So thank you very much. Thank you, my dear students.